Hi, welcome back to Missing Chemistry. This is electron configuration of 10SN. Oh, wait a minute. SN and 10? That doesn't make sense. Oh, yes, it does, because 10 had another name long time ago. I believe it was Stantonus. So that's where the SN comes from. Some of the elements and their element symbols do not match up. Just to kind of give you a little hint there. And that's probably because they had an earlier name. All right, so now, let's get started. Hey, speak of which, 10, T-I-N, by the way, not T-E-N, happens to be element number 50 on the periodic table. So let's write down 50 for our atomic number. Rules, snarls. And its AMU is going to be rounded off to 119. So that means we have 50 protons, 50 electrons because it's electrically neutral. What about our AMUs? AMU is 119, but if we want to know neutrons, we got to take the AMU minus the protons, right? So we go 119, that's correct, minus 50 will give me 69 neutrons. Pretty darn snarly, as I would say. By the way, you know snarly's the new cool, right? You mean you don't know that? Oh, come on, man. It's like in the 1920s, the cat's meow was cool, right? Now, it's snarly. All right, so anyway, getting back to some other realities here. Before we do electron configuration, it's important to remember that the S subshell can only hold 2 electrons. The P subshells can hold 6 electrons. The D subshell can hold 10 electrons. And yes, the F subshell can hold 14 electrons. Use the off-ball principle, which clearly states fill the lower shells first before you fill the upper shells, and use the diagonal rule. What is the diagonal rule? Well, we just follow the red arrows until we run out of electrons. Let's get started. Okay, 1s2. Man, that seemed really hard. 2s2. This looks pretty easy. 2p6 and 3s2. We go 2p6 and 3s2. 3p6 and 4s2. Wow, this is so cool, right? Hey, 3d10, 4p6, and 5s2. Wow. We're using up those electrons pretty darn fast. Now we go 4d10 and then 5p2. And then, of course, we're out of electrons. Amazing, isn't it? You thought electron configuration was hard, but you know what? It's only hard if you make it hard. Remember, use that diagonal rule. It's there for a purpose. Hund's rule, speak of which, tells us that the suborbits can hold an up arrow of one suborbit, and each of those one suborbits, depending upon what shell you're using, and then you start the down arrows. Well, it's better to look at it this way. Look, S only has one suborbit, right? Up and then down. Hey, 2s, up and down. Now here's a great example of it. 2px, 2py, 2pz. 3 suborbits for the p's, right? 1, 2, 3. Every suborbit has an up arrow. Now we're going to start the down arrows. 4, 5, and 6. See how easy that was? 3s, same thing, right? So let's go on and do this. Oh yeah, oh yeah, oh yeah. This is pretty cool. And it doesn't matter if you have 3 subshells, 5 subshells, 14 subshells, whatever. It always works. Actually, you're going to have 7 subshells. You're not going to have 14 subshells unless we invent something way down the line, way past Ogasium, which is element 118. So let's go. See how easy that is? Man, it doesn't get any easier than this. And again, 40x squared minus y squared, 40xy, 40yz, 40xe, 40z squared. Fill those in. See that? Almost running out of electrons, guys. We've just got a couple more electrons left. Matter of fact, 2 of them. So we go up and then up. Wasn't that snarly? Okay, now, we're getting really close to xenon, but xenon is not the noble gas for 10. It's still going to be krypton. Because remember, xenon comes after 10, so you can't use it. And we're going to use our valence shell to go on the end of this. And we have to put it in numerical order. So it would be 4d10, 5s2, 5p2. What about our quantum numbers? Well, Pauli's exclusionary principle says that no two elements can have the same set of quantum numbers, right? Right. So it's in the fifth period because it's in the p block. It's located somewhere right in here. Approximately. All right, so if it's in the p block, the angular momentum number, of course, is going to be 1. And we said the principal quantum number was 5. So we need to put that one. Now, what about our magnetic number? It happens to be the second one over. So you go -1, 0. And that last arrow, right here, that last arrow is going up, right? It sure is. That's what it looks like to me. So that's going to be 1/2 positive for our spin number. Pretty darn cool, I'd happen to say. All right, well, guys, you be snarly, and we'll see you back here at Moosine Chemistry.